On Saturday, we have done the makeup class, and this is a very important class actually. I hope that you have viewed the videos or attend the lesson in person. The topics that we covered in the makeup class was concerned with the moment of inertia. So in the lesson last Monday, we talked about the moment of inertia, and we further elaborate on it on the makeup class this last Saturday. So in most of the case, the moment of inertia have to be calculated by integration. But the concept of the moment of inertia is that you have to consider the distribution of the particles as well as the mass of the individual particles in a rigid body. So the idea is each of the particle would be contributing to the moment of inertia in the form mi/ri squared. M is the mass of that particle, and r is the distance of that particular particle from the axis of rotation. So the location of the axis is very important because that would affect the values of r for all the particles and therefore affect the final value of I. I as the unit, by the way, I as a unit of kg times meter squared. So in most of the case, you would have to do integration in order to find out the moment of inertia. For some special situations, we have prepared a table for you to take reference. And this table summarizes the moment of inertia for various situations. As you will see in this table, many of the I are followed by Cm. Cm at here refers to center of mass. So as you would notice, the axis of rotation for many of the cases, they are passing through the center of mass. Say in the case of a cylinder, which could be a long rod or a thin disc, depending on how long it is along the axis of a rotation. So ICM is 1/2 mr squared. Moment of inertia is given by this value. And of course, the center of mass of this rod is right in the middle along the axis and halfway of the length of the cylinder of the disc. On the other hand, for the rod rotating in this direction, so you rotate the axis by 90 degrees, the center of mass is in the middle. So the center of mass in the middle is given by 1/12 ml squared. That is slightly different already compared with the previous equation. But not all the situations would have the rotation about the center of mass. Say you could move the axis of rotation from the center of mass to the end of the rod. So the calculation or the integration has to be done starting from the beginning. Or if the axis of rotation, the new axis of rotation is parallel to one that passes through the center of mass, say in these two cases, the axis of rotation, they are parallel. It is just that it has translated from the center of mass to the end of the rod. From this case to this case, you are moving the axis of rotation parallel along the length of the rod. So it moves by a distance L/2 along the rod. So the two axes of rotations are parallel. In that situation, the moment of inertia for these two cases, they could be related by what we call the parallel axis theorem. The idea is you have a body, that is rotating about a certain axis. And of course, if this axis passes through the center of mass of the object, you have a certain moment of inertia. If by some chance the object is not rotating about the is not rotating about this axis that passed through the CM, but it is rotating through another axis parallel to the original axis. So these two are parallel. They are parallel to each other, and the distance between the two axes is d. Then the new moment of inertia about the new axis could be related to the moment of inertia about the center of mass by the equation as shown above. M is the total mass of the object. D is the distance between the two axes, which are parallel to one another. This is very important. The two axes are parallel to the axis through the CM. And in that case, you could use the parallel axis theorem. The parallel axis theorem is this one. So in the lecture notes, we have the example. We have the example of moving the axis from the one passing through the CM to the end of the rod. With the integration, we could calculate, of course, the answer. But with the parallel axis theorem, we could also find out that the answer is valid. And also in the tutorial question 4, we have seen a question in the tutorial question 4. Let's see. So tutorial question 4, we have seen this example, which is a three-dimensional cross, if you like. And the axis of rotation is not through the center of mass, but at a distance L/2 from one of the axes. So to make the calculation simple, we could firstly calculate the moment of inertia about the y-axis, which is going through the center of mass for the whole structure. And then we translate the axis by a certain distance parallel to the original axis we did the calculation. And in this way, we could calculate the new moment of inertia for a structure rotating about the end of one rod. So that is the idea. Okay. Now, and then in the makeup lecture, we also talk about the equivalent of the force in the rotational motion, and that is torque. The idea of torque, of course, is to change the acceleration, but is to provide an acceleration in the rotational sense. So the acceleration could be positive or negative, depending on whether you are slowing it down or speeding it up. And the torque is dependent on several things. The torque is dependent on several things. The torque depends on the size of force that is applied to the object, and it depends on the distance between the axis of rotation to the point of application of the force. So it depends on the magnitude of F and the magnitude of R. Finally, it also depends on the direction in which you apply the force. So if the force is perpendicular to the R vector, in this case, if the force is perpendicular to the r vector, you provide the maximum turning effect. It provides the maximum turning effect. But if the force is parallel to the r vector, as you would justify from your common sense, when you just apply the force along the spanner, it does not turn the nut. You can only turn the nut when the force is perpendicular to the spanner. So only the, if you like, only the component of the force perpendicular to the r vector contributes to the torque, or the torque is just the product of the force and the perpendicular distance of the force from the axis of rotation. In both cases, it could be written as RF sine phi. It could be R times F sine phi. So you are considering only force component parallel to the spanner, or R sine phi times F. R sine phi would be the perpendicular distance of the force from the axis of rotation. So all these are considering the size of the turning effect, and that is the torque. Finally, there is one thing. The turning effect, or the force, this type of a turning force or the torque, it is a vector. So it could be generating a positive angular acceleration or negative angular acceleration. By convention, we treat a torque that causes anti-clockwise rotation to be positive, and a torque that generates clockwise rotation to be negative. That is our convention. In any case, the torque, which is the product of the force and the distance, it has a unit of Newton meter. It has a unit of Newton meter. Some of you are asking the questions. Well, can we just calculate them separately? I don't know what it is meant by them, so I leave it a little bit. Well, the PowerPoint is in the Blackboard, so it is in a second set of lecture notes. Can we explain about the previous question about the free watts? I'm afraid I'm not explaining it here because I have a lesson to go. The answers would be posted on the Blackboard after. Well, I will put the answers for question Unit 10 on the Blackboard later today, if I could finish the teaching of the Unit 10. Okay. So we talk about the torque, and of course, we have to be careful about the direction of the turning effect generated by the torque, just like we have to be careful about the direction of the force. It has to be the net force. So similarly, it has to be the net torque that is related to the acceleration, angular acceleration of the object. So the idea is we have the equivalent of the Newton's second law in the rotational form. So the net torque would be generating an angular acceleration, and the size of the angular acceleration is dependent on the moment of inertia. So the linear form would be F equals to ma. Here, the rotational form, torque equals to I alpha. Once again, the torque is the net torque, just like the force is the net force. So we also cover the idea of the work done in the rotational motion. In the case of the linear motion, work done would be equal to F times ds, force moving along the displacement direction. So it is a dot product. So at here, we try to derive the work done in the rotational form, and we find that actually the work done for the rotational form has a similar format. It is torque times the angular displacement. Torque times the angular displacement. So that is the important thing. Of course, if the torque and the angular displacement are in the same sense of rotation, that would be a positive work done. If they are in opposite direction, that would be negative work done. When you have a work done, you would be changing the motion of the rotating object, and that would be converted into rotational kinetic energy. So we have talked about it before. Ke for rotational form, 1/2 I omega squared. And here we have summarized a number of equations for linear and rotational motion. Now, at the end of this set of notes, we would have a extension of the rotational motion, but here it is a slightly complicated form, although it is more common than just simple rotation, because you will see it every day whenever you go down the street, and that is objects rolling on the surface. So if you try to roll, for example, a metal can or a corn on the surface, you will see that the object, of course, it is performing a rotational motion, but at the same time, when you have the corn that is rotating, the center of the mass for the corn is actually moving as well. So here, we cannot see it very clearly, but it is the person holding a cylinder, and the cylinder is moving on a flat surface. It is moving on a flat horizontal surface. So on a particular point of the cylinder, it would map out a trajectory, it would map out a path as shown in the red. So because the cylinder surface is rotating, so the particle or the particular point on the surface of the cylinder would be from time to time moving downward and move upward again. During this time, the center of the cylinder, the center of mass for the cylinder would be moving forward. So it is not just the particle moving downward and upward, but it would be moving forward as well. So it would map out a path, what we call a cycloid. We are not particularly concerned the exact equation form of a cycloid. If you are interested, you could definitely find it on YouTube. But here, I just show you that when you have an object that is rolling without slipping, when you have an object that is rolling without slipping, that means it does not slide on the surface. The center of mass is, of course, moving in a linear fashion, but at the same time, particles on the surface of the cylinder, they will be moving as well. So what is the actual motion form? In fact, let us try to take a look at the situation. Here, you have a cylinder that is performing a rolling motion. So from time to time, say at here, the cylinder is rolling in the clockwise sense, and therefore it is moving forward. For over a certain angle of rotation or certain angular displacement theta, the point on the surface of the disk would be covering a distance s. And because the object is rolling, it would be directly converted into the linear motion. So when the object is rolling on the surface, it would be, of course, covering a certain angular displacement, but linearly, there would be a translation as well. This particular translation in the horizontal sense, it is related to the angular displacement by the equation we have seen, S equals to R times theta. think about it. If the cylinder has rotated by 2 pi, in terms of angle, if the cylinder has rotated by 2 pi, that is 1 revolution, it would have moved through a distance of 2 pi r. So it has gone through a distance of 2 pi r. So this equation is justified. And because the surface of the cylinder has moved by a distance of 2 pi r on the surface, that means the center of mass for the cylinder should also be covering the same distance. So the center of mass has the linear motion. The center of mass has a linear motion that is related to the angular motion. Center of mass has the linear displacement that is equal to actually ds over dt. And s is related to r times theta. So we could take out the r because r is the radius, and that is constant. So it becomes d theta over dt, which is equal to omega. So we could now, for the case of a pure rolling motion, rolling without slipping, without sliding, the center of mass is moving in relation to the angular rotation, angular speed. Similarly, the acceleration for the center of mass is related to the acceleration of the rotational acceleration of the cylinder. So this would be very important to connect the linear motion of the center of mass as well as the rotational motion for the object about the center of mass. In fact, when we consider the rolling motion, it is possible for us to think of it in a way as a combination of 2 types of motion. First, we have the rolling motion of the cylinder, pure rotation. The pure rotation means that it does not consider the movement for the center of mass. It assumes that the center of mass is stationary. So in this type of a pure rotation, of course, all the particles would be moving with a speed that is equal to r times omega. If the cylinder is rotating with the angular speed omega, then all the particles on the cylinder would be rotating at the speed of r times omega. Velocity, of course, is different for any point on the cylinder. At the bottom, it is moving backward. At the top, it is moving forward. Now, at the same time, you have the cylinder that could be considered moving in a linear way. If you consider the center of mass, it is moving linearly. It does not rotate for the center of mass only. So we could consider it as a pure translation, just like you have a block sliding on a flat surface. And the center of mass is moving with a speed or velocity that is equal to VCM. But if you have an object that is just rolling without slipping, basically, when you have an object that is rolling without slipping, you are converting all the rotational motion into a translation for the center of mass. So at the point of contact between the surface and the cylinder, the translational motion for the whole object, which is equal to VCM forward, it is equal to the velocity of the particle at the bottom, but it is moving backward. So at the point of contact, velocity of particle is 0. with respect to the surface in which the object rolls. So at the point of contact, the relative motion between the cylinder surface and the ground would be 0. It is just the surface of the cylinder in contact with the ground that has a relative speed of 0. The center of mass still is moving with a velocity v(cm). On the other hand, the top particle, which is under the relative motion of pure rotation with respect to the pure translation. So it would be the addition of the two velocities to an independent observer from the outside. So it would be the total velocity to the independent observer from the outside equal to the velocity of the center of mass plus r omega, which becomes 2v(cm) for the particle at the top. Okay, once again, if you are a particle sitting right on the cylinder, you would only experience a pure rotation. So to a particle on the cylinder, the top particle would be experiencing a relative motion relative to center of mass, that is equal to r omega. The particle at the bottom, it is moving backward relative to the center of mass with a velocity r omega in the backward direction. At the same time, due to the rolling motion, the whole cylinder would be moving forward with v(cm). So all the particles would be moving forward with v(cm). So altogether, to an independent observer from the outside, he would see the center of mass to be moving with v(cm), but the bottom particle is moving with 0 velocity. The top particle would be moving with 2v(cm). So that is the combination for the motion. On the other hand, if we are trying to consider the energy of particles or energy of the rolling object, we could consider it to be the contribution from various types of motions. The idea is like this. You have an object that is rolling. So the center of mass is moving in a linear way, so it has a linear kinetic energy. But it is not the same as a purely linear motion. You have the object that is also rotating about the axis of rotation. So you have to add up the energy for the two different situations. So that is why you would have the total kinetic energy equals to 1/2 mv(cm) squared. That is the linear kinetic energy due to the linear motion for the center of mass, and 1/2 I(cm) omega squared. That is due to rotational kinetic energy for the object rotating about its center of mass. So we could actually, when we consider the energy of the particle, we could actually separate them into linear form and rotational form. So that is the important message here. When we consider the energy of a system, if it involves different types of motion, we could separate them into different forms. Yes, some student asked at the bottom point P, the velocity is 0. It is exactly because the linear motion velocity cancels the rotational motion velocity. So they are offset one another. So That is why when we talk about the frictional force in the few chapters ago, we say that it is not a kinetic friction because the object is not sliding on a surface, but it is rolling. So there is actually zero velocity at the point of contact. And the frictional force in that case would be a static friction instead of a kinetic friction. Okay, now let us come back to the example in last example in the unit 10, and that is concerning the rolling of a sphere down an inclined plane. That is a rolling of sphere down the inclined plane. Now this sphere has a radius r, and it is rolling down an incline with a slope of length x. As I've said, at the surface at the point of contact, the velocity is 0. So the static friction is actually causing the torque to, you see. So the static friction is trying to prevent the ball from sliding forward, and it is therefore generating a torque that helps to get the ball rolling down the surface. So this would be the friction produce a net torque required for the rotation. And there will be no loss of a mechanical energy at the point of contact because the ball is rolling, so therefore no relative motion at the point of contact. Therefore, there is no mechanical work done. And of course, in reality, if you have the ball that is deformed, then there would be relative motion, and this would be the frictional force that would be causing a loss of energy. But if the ball is perfectly spherical and rigid, there should not be any loss in the energy. So here we try to figure out how the kinetic energy is coming from the rotational energy and the linear kinetic energy. So here we write down the equation. K is equal to 1/2 ICM omega squared plus 1/2 m VCM squared. Omega is related to VCM by the connection equation. VCM equals to omega r. So omega equals to VCM over r. And with the suitable combination of the terms, we could write down the total kinetic energy. And where does the kinetic energy come from? It must be coming from the loss in the gravitational potential energy. So in this way, we could determine the linear speed, linear velocity of the ball when it is rolling down the surface. Now, this equation would be quite different from the case when you have just a particle sliding down a smooth surface. So here you see the moment of inertia actually plays a part in the calculation of the final speed of the particle. And here it tells you how the center of mass acceleration is calculated. It is not exactly g sine theta as you would expect when you resolve the force components, but it is slightly less than g sine theta because in a certain sense, part of the acceleration is used for generating the rotational acceleration of the sphere. So it would not be exactly the same as the particle sliding down a smooth surface. Some of the classmates are asking about the frictional force producing the net torque. So at here, if you have the sphere that is sliding down the surface, of course, it would be generating a motion in this way. So if it is sliding down, the velocity, it will be like that. But of course, the surface would not allow the sphere to slide down so easily. So in that case, to prevent the relative motion, the surface have to provide a frictional force that prevents the sphere from sliding downward. And in a certain sense, that prevents the relative motion at the point of contact. So this frictional force would cause a rotation of the sphere, and that is why the sphere would start rolling due to the presence of the frictional force. If it is a completely flat surface, completely smooth surface, then the whole sphere would just slide down without rolling. It would just slide down, just like a particle. But because of the presence of friction, it would start rolling, and it would be rolling forward, as you would fully expect from the daily life case. So at here, what is meant by the contact point is at rest relative. Not quite sure what it is about. It is the contact point for the relative motion. We are talking about the contact point. And for the sphere like that, the contact point is just the lowest point, which is P in the case here. So in the case of a rolling, you would have the when can it roll with constant velocity? Okay, one by one. When can it roll with constant velocity? It would not be, because it is under a constant acceleration. It would not be rolling with constant velocity. For the case of, for example, I show it here. This is a constantly accelerating object with the center of mass accelerating with this value. So it would not be a constant velocity motion. It is a solid sphere, so we have a it is a sphere, so it is a 2/5 mr squared. So it refers back to the table of the moment of inertia. At here, this one. Well, we do not think we calculated. We calculated the acceleration. Actually, you could do the calculation as well. It has a initial velocity equals to 0, final velocity VCM given by this one. So you could find out what is the corresponding acceleration. VCM equals to this one, just to show you the connection between the theta and a VCM. Okay. Now, before the end of this class, let us try to take a look at a tutorial question, and that would be question number 5. It refers to a cylinder that is rolling without slipping on a horizontal surface. And at a certain instance, the center of mass has a speed of 10 meters per second. So the situation, it is just like this. Okay. Okay. You have a sphere rolling on a horizontal surface, and it has a mass equals to 10 kg, and it is rolling without slipping. So if it is rolling, then you could relate the linear velocity for the center of mass to the angular velocity for the object, for the rolling object, by this equation. So let us just, well, I better go back to the tutorial question and see. Okay, coming back to the tutorial question. You are trying to determine the translational kinetic energy. So translational kinetic energy is just a 1/2 mv squared, which the V is already given to you is 10 meters per second. M is 10 kg, so it is quite straightforward. The rotational kinetic energy has to be determined by I equals the rotational kinetic energy is determined by 1/2 I omega squared. For a cylinder, I has to be determined by the equation at here for a cylinder. If it is rotating about its axis through the center of mass, like that, so the moment of inertia for a rolling cylinder, if, well, you use a bit of an imagination and turn it 90 degrees, you know it is referring to a rotating or rolling cylinder. I is equal to 1/2 mr squared, and omega is equal to V over R. So the calculation would give you the rotational kinetic energy of 250 joule. So I better just show you the solution at here. It's not very convenient to use Zoom to teach, but anyway. So it is question 5. The linear kinetic energy 1/2 mv squared, rotational kinetic energy 1/2 I omega squared. Omega is equal to 3 over R for a rolling cylinder. So it is 250, and the total kinetic energy is just 750 joule, which is the sum of the two kinds of kinetic energies. Okay. Right. So I would finish the teaching for the Unit 10 at here.